Hello friends, welcome to Physics with Sanmitra and I am Sanmitra Bhomik and today we are going to learn about free body diagram. This is a very important topic in Newton's laws of motion and you need to learn this topic very well in order to solve any problem in Newton's laws of motion and also in the further chapters, upcoming chapters in mechanics and other topics, because this is the basic. If you don't know how to analyze the forces, how to understand that which force will act in which direction, then you cannot solve the problem further, because this is the absolute basic. And please pay attention in this lecture. If necessary, please watch the parts again and again, because in this part students do have problems and they do not mend them and they go further, and naturally they face problems in the later chapters. So let's begin. So what is free body diagram? Free body diagram is a method to separate the forces acting on an object. Suppose I have given you a simple thing like say a block of mass m that is lying on the ground, and I am telling you if I am pushing the block it will go forward, move forward with an acceleration a. That is what Newton's second law of motion says, and also when I am applying the force it is moving. Now for this simple system you will not understand the significance of free body diagram. But say I am giving you a complex system like say this. I am giving you a complex system. There are 3 discs, all 2 discs, and on top of that there is another disc. So now if I ask you that what is the contact force between these 2 discs, say here the contact force between these two, contact force between these two, and the contact force between these two, then you will understand the significance of Newton's laws of motion. Okay, so what do we exactly do in case of free body diagram? Free body diagram, what we do is that we separate the forces acting on an object. That means actually multiple objects associated with one another are separated or freed from one another. That means we are having many objects on one on top of other, or connected in, or associated or connected in any manner. Now we have to free them, we have to separate them, and then we have to separately analyze each object so that our problem gets simpler. So I have given an example here. See, I have a mass m. Say here I have a block of mass m that is lying on the ground. Now here what I have done is that I have separated this object. I have separated this object from the ground. I have mentally, see, here is the one thing, I am not physically putting it upwards, holding it up to a distance. I am not doing that. I am mentally separating them. That means this object is actually connected to the ground. It is lying on the ground, but I am purposefully drawing it in such a manner that it is being shown that it is off the ground, it is having some distance from the ground. So what are the forces acting on the object? See, there is an mg, that is the mass into mg, and there is normal reaction n. Now what is this normal reaction? Suppose this block of mass mg is kept on the ground, or suppose, let me give you an example. Suppose you are sitting on a chair. Let me draw it. Suppose you are sitting on a chair. Now let me draw the chair also. This chair I am drawing with orange. This is the chair and your feet is off the ground. Your feet is not touching the ground. Now let's say your weight is 55 kilo. And let's say g is equal to 10 meter per second. Now what is the weight acting on you? The weight acting on you will be distributed force, but I am assuming your center of mass is somewhere here, so it will be 550 Newton. Now a 550 Newton force is acting on you. In Newton's second law of motion we have learned that F is equal to mass into acceleration. We have this mass that is 55 kg. We have force that is 550 Newton, that is the weight with which the force with which the earth attracts due to its gravitational force, that is 550 Newton. Then where is the acceleration? but the acceleration here is 0. A is 0. So how to account for that? Because you are sitting on the chair and you are in equilibrium with respect to the ground. Now, so there must be another force that is acting on you from the chair, which is balancing this 550 Newton force that is acting upward, exactly equal and opposite. That equal and opposite reaction from the ground or from any contact surface, that is known as normal reaction or just reaction. It may be equal, it may not be equal and opposite, but the force, the contact force that is acting from the surface, that is called reaction. Now this reaction, if it is, or the component of the reaction which is perpendicular to the surface, that is normal reaction. We will talk about it later, what happens if the reaction force is not exactly normal to the surface, but now for this time let us focus only on normal reaction and not just an inclined reaction or such like that, but normal reaction. So here the normal reaction is N, that is acting from the ground, and equal and opposite reaction will be acting on the ground. See, this normal reaction force is an internal force. It will generate equal and opposite pair, like N is acting on this block and then an equal and opposite N that will be acting in line with the block. See, I have drawn here, both the N are in line. I am not drawing N here and other N here. This is not correct. Okay, it will be in line. So now our analysis becomes easier. We will solve a few more complicated situations, we will analyze them, then you will understand the significance. Okay, let's move forward. Okay, now let us increase the complexity slowly. We have two objects. One is mass m1, other one is mass m2, and they are situated in the ground. Now, our first job is to separate them. See, this is m1, this is m2, and the ground. They are not actually separated, but we are mentally separated them, as we have discussed earlier. Now the forces. There is a m1g that will be acting downwards, and just see for the contact force, just see the surfaces it is touching. Like see this m1 block, this block is touching only the lower block, that is m2. So this will be n1, and an equal and opposite force will be acting here, that is n2. Okay, in this force, this is done. This m1 and this n1 is done, and it is at rest, so this acceleration will be 0. We will talk about equilibrium later in a later video. The objective of this video is only to make you identify the forces and to correctly make you draw the FBD or free body diagram. This is n2. Now exactly from the center of mass we will be drawing the weight. See, I have drawn it here just to make the figure neat. Actually it will be from the center of mass, and if this is an uniform block, then it will coincide with the geometric center. We'll discuss about this in a later video where we'll be talking about center of mass. Okay, now what are the forces? See, this block mass m1 that I have separately analyzed. It's not that we are analyzing it together. Many students will connect these two. They will do like this. They will make it m1, they will make it m2, and they will do all sorts of calculations here. That is wrong. Please do not do like that. Separate all the blocks and then do it. If it takes time, let it take. Now, this is n2 and the weight is mg, and this block m2 is touching two surfaces. One is this block, the upper one, other one is the ground. So upper one, the contact force is n2, we have already got it. The lower one, sorry, n1, we have already got it. See, this is n1, this is n1, both will be equal and opposite. This will be n2 from the ground, and an equal and opposite reaction will be acting on the ground, and I don't think so the ground is touching anything where else, at least in this context. So I have drawn everything neatly in the right hand side. So this is our first free body diagram, or the first block. This is for the second block, and this is for the ground. I hope now this is clear how we separate each and every block. Now, what is equilibrium? We'll discuss equilibrium is, or translation equilibrium is, net force acting on the net external force acting on the particle or the object is zero, or net force is zero. Net force acting on the object is zero, and if net force is zero, then mass into acceleration is also zero, implies that A is also equal to zero. So there is no acceleration out here. So what are the forces acting? Now let's see how we apply these concepts. How we apply. Just see here. See for the block 1. For block 1, the downward force is, see here, it is mg, and the upward force is n1. Is there any other force? No. And this is in equilibrium, perfect equilibrium. So we'll write it like this: mg, m1g, this is m1g minus n1 is equal to 0. So m1g is equal to n1, our first equation we have got. For second block, n1 is down, see, n1, m2g and n2. n1 and m2g are downward and n2 is upward. So let me assume downward as positive. We can assume anything. By this stage you must be knowing n1 plus m2g minus n2 is equal to 0. So we have two variables, n1 and n2, and we have two equations. Now we can solve because they are in equilibrium. And suppose you are asked to find the contact force at ground, so that will be n2. Suppose you are asked to find the contact force between block 1 and 2, that will be n1. So I hope now this is clear to everybody. Next, our next example is, we have two blocks lying horizontally alongside. Now we are applying a force F on the block. Now let's analyze. So what is our first task? Our first task is to separate the objects. So I will draw this object first, that is M1. I will draw this object first. Just excuse me. So, and we will also draw the next object, that is M2. This is M1 and this is M2. And the ground, because they are lying on the ground. See, the ground also I have somewhat separated. See, the distance I have kept here between ground and the blocks. See, the first force that is acting on this one, that is F. See, I have drawn here also. I am showing from the figure. This is F. I will be analyzing M1 first, then M2. At first M1. Now forget about M2. When you are analyzing one block, you will absolutely, I am writing here, you can note it down in a notebook, forget the other block. You just need the contact surface, that's it. The angle of the contact surface, I will tell you how is it. You just need to know what the other blocks, which other blocks is your current block touching. Otherwise you will forget that what forces are acting on the other block, etc. You just focus on your own, on the block of consideration. Now it is 1. See, F is acting from top to bottom, that is M1G. Now see, this block M1 is touching two surfaces. One is the ground, the other one is block M2. Now just see here, from the ground there it is N1, you can see, and equal now N1. Just a minute, let me specify this a little bit more. Let me see, this is the object 1, this is the object 2, and our ground is our object 3. I hope now you get me. In object 1, just see, if the normal reaction is coming from ground, and another reaction force, that is R12, that is the reaction force between surface 1 and surface 2, or block 1 or block 2, that is acting in a horizontal direction. This is these are the forces that is acting on block 1. Now let's look at block 2, this block. In case of block 2, this reaction force, first of all let us analyze what are the contact surfaces and what are the forces acting. First of all, the weight will act, that is m2g. There is nothing new in that, m2g. Now the contact forces, it is touching the block m1, so r12. Now see, r12 and or maybe r21, you can say r12 and r21 are same, or I'm showing them both by r12. R12 and r12, these both will be, you can say they are equal and opposite and will be in line with each other. Now this is N1 and N2 from ground, sorry, N2 from the ground. It is touching the ground, so ground will exert a force N2. So that's it. And now the ground, what surface are touching? This block M1. This block M1 is touching the ground and this block M2 is touching the ground. So N1 will be given, a force will be exerted from the block M1 to the ground, and N2 will be exerted from the block M2 to the ground. Okay. So this is, we will separate each object and we will analyze the forces. If you do not understand any part, then please rewind a few seconds and watch it all over again, because this much understanding should be clear for the further video. And also you can leave in the comment section if you find any doubt. Okay, now up to this much. Suppose this block of mass m1 and m2 is moving with an acceleration a. This is smooth, there is no friction. I will discuss friction in a separate video in the upcoming videos. Now let's analyze this. This is force F. See, if you had seen my constraint motion playlist, you will be knowing that m1 and m2 both are moving together. So this is a kind of constraint motion, and both will have the same displacement, same velocity, and also the same acceleration. If you are not understanding this, then please go through our constraint motion playlist and things will be crystal clear. Now, so this acceleration for m1 will also be a, and m2 will also be a. Now just see, this object or this system, this is in equilibrium in the y direction. See, these blocks, these are only moving in the x direction, that is a constraint. These are not moving in the y direction. This block M1, it is not moving upward or downward. I hope this much is understood. This is not moving upward or downward, it is only free to move along the x direction. Obviously, if I put some force upward, then definitely if it can overcome the gravitational pull or gravitational force, if it can lose the contact. I am not talking about that. But in this case, it is moving only in the x direction. Okay. Now, this force is F, and this is acceleration A, this is acceleration A for both. Now, this is in equilibrium in the y-axis, summation of Fy is equal to 0. Now for block 1, what I told you, analyze each block separately. While writing the force equilibrium equation or force equation, or while analyzing the equilibrium condition or analyzing the free body diagram, forget about the other block. Just know the contact surfaces. Fy is equal to 0. So now for block 1, I can write m1g minus n1. These are the two. Suppose this is my x-axis. Let me define the axis. This is the x-axis and this is the y-axis. So in the y-axis, along the y-axis, m1g, I'm taking it as downward as positive. We can take anything. And upward as negative. m1g minus n1 is equal to 0. And for the block 2, I can take as m2g minus n2 is equal to 0. that gives n1 is equal to m1g and n2 is equal to m2g. Both should be equal because there is no acceleration in the y direction. Now, let me remove the axis. I hope you have written it down. Now, let's say in the x direction. In the x direction, there is an acceleration a in both the blocks. So, it is not an equilibrium. Now we'll apply Newton's second law of motion, that is F net is equal to mass into acceleration. See, what is the direction of acceleration of A? That is in the right hand side. So net force will be on the right hand side. See, F is on the right hand side, R12 is in the left hand side. These are the two forces that is acting in the along the x-axis. So definitely, since the F is in the right hand side, so I will write the net force F will be larger, F minus R12. This is the net force, F net is equal to mass m1 into acceleration A. Okay, this is the equation. Now this is for block 1. Let's analyze for block 2. In block 2 there is only one force, that is R12, that is acting on the x direction, and the acceleration is same, that is A. So I can write for block 2 R12 is equal to m2 into A. Now if we solve these two, we will get force is equal to m1 plus m2 into A, or A is equal to F by m1 plus m2. So these two are moving together, both we can consider together as a mass of m1 plus m2, and that is acted upon by a force F. Then the acceleration will be F by m1 plus m2. And if you are asked to find the contact force between the two blocks, then you have to find R12, that is m2 into the value of A you got, you substitute here and you will get the answer. This is very basic, and I hope this is crystal clear to you. Now let's increase the complexity slowly. See here, we are applying a force on the block M, but with an angle of theta with the vertical. Now let's draw the free body diagram. The first and foremost rule for drawing the free body diagram is to free the body, is to separate the body. See this mass M, block of mass M. See here the block of mass M. What we'll do, we will just separate it from the ground like we have done here. We have separated it from the ground mentally, not physically. Now we will forget about the other block and we'll focus on only the block of mass M. We'll focus on only the block of mass M, and we'll remember that it is making contact with the ground or any other object if it had been making contact, but we will not focus on them. What are the forces acting on this? The first one is mg, the next one is F, that is making an angle theta, and it is making a contact with the ground, so there will be a reaction force from the ground. In case of smooth surfaces, there is no friction, and the contact force will always be perpendicular to the surface of the surface of contact. It is making a contact with a plane surface here as shown, so it will be perpendicular to the plane surface. Now exactly that is the thing what I have drawn here neatly. I have drawn this part neatly here. So F is acting on a direction, say with a direction theta with the vertical. Mg is acting downward. See, Mg should be acting from this point to this point downward, center of mass. I have not shown it because it will be untidy. That is the only reason. Otherwise, if you have to show, then you can show like this. See, Mg and Mg will be acting exactly from center of mass. I am just showing it here like this because I am just displacing the vector up little bit upward, just to make the diagram neat. Now this is our object of consideration, and the ground is The ground is being acted by a force N. That is the contact force between the object mass M and the ground. Now, let me resolve this F into two components. This will be F cos theta. This will be F sin theta. This is simple trigonometry, and I hope you can understand this, how we resolve this into F cos theta and F sin theta. Now, this is in equilibrium. Since there is no force acting on the, so there is no net force or no acceleration. Okay, in the y, okay, we don't know this is in equilibrium or not. Now let's see. In the x direction, in the y direction, what are the forces? We have mg, we have n, we have F cos theta. Now let's write the forces. Let's assume upward, downward as positive. Let's assume F net. This is the F net in the y direction. F net comma y. F net comma y. That is mg minus F cos theta minus n. This F net y will be 0 if it is in equilibrium. Now, suppose F net is 0, this part I am taking as 0, and so I can write normal reaction as mg minus F cos theta. This is mg minus F cos theta, this normal reaction. Now just see. This normal reaction depends on the contact on the ground. Suppose I am increasing this value of F, so normal reaction will decrease. I am going on increasing this value of F until this F cos theta will become equal to mg. Then the normal reaction will be 0. At this point, it will lose contact with the ground. This will lose contact with the ground at that value of F. We can do the same thing with theta also if F is sufficiently large. Suppose we are increasing theta up to a point that F cos theta will become equal to mg. At that point, this n will become 0 and this will start moving up. Then F net will become in this direction and it will start moving up. Now let's see from here itself. This is F sin theta. Is there any force to oppose this F sin theta? There is no friction. So this is the only force that is acting in the x direction. So this is not in equilibrium. This object is not in equilibrium. It has a net force F sin theta provided this contact is maintained with the ground. That means n is not equal to 0. Suppose n is greater than equal to 0, then our F net will be, if these two are cancelling each other, this one and F cos theta, if these three are cancelling each other, if I can say, then F sin theta, F net will be equal to F sin theta, and acceleration will be F sin theta by m in the x direction. Okay, I hope this much is clear. For this much analysis is clear. Now, what is the reaction force from the ground? In the absence of friction, normal reaction acts perpendicular to the surface, as I have told you already. Suppose I have an object here, it is kept on the ground, the normal reaction will be perpendicular to the surface. This surface is here, the normal reaction will be perpendicular. See here, I have kept an inclined plane. And in the inclined plane, I am putting an object here. What is the inclined plane? It's a plane surface, a flat surface which is inclined by an angle alpha. That is, it is not flat with the ground, it is having some inclination with the ground, that is angle alpha or theta. Say theta, here it is theta. Now see, while drawing the free body diagram, we'll just consider only one object. But you need to know the surface as well. So I have shown the surface with the help of dotted lines. Whenever I will be showing the surface with the dotted lines, remember it is just there to show you the reference. I am not considering that object. I have forgotten that object. But I am just showing the remnants of that object, like say the dotted lines. Okay. Now this normal reaction force N is acting perpendicular to the surface of the contact. This one. It is acting perpendicular. Now say if I do the force analysis on this one, there will be an mg downward, exactly downward, and n will be upward. So for some students there is a confusion that mg is equal to n. This is not true. This is true only for the flat surfaces where mg and n vectors will be anti-parallel. Only on those surfaces. But when there is an inclined plane, n will be something like this. N will be something like this and mg will be vertically downward. That's it. In case of round objects, for smooth surfaces, reaction force only normal reaction acts towards the center. See, on smooth surfaces only normal reaction is there, no friction. And in case of round object, for smooth surfaces, normal reaction acts towards the center. It will be in line with the center. See why? It is very simple. See the ground, say I have shown the ground with the dotted dots. Just see. The ground is like the tangent and this is the normal, and the normal passes through the center. I can say this normal will pass through the center. So the normal reaction will also pass through the center. This is just a geometric property. That's it. Nothing so special in this. But students get confused sometimes, so I have covered it. See. Now the actual difficulty level starts. Draw the free body diagram for the following arrangement of identical disks of mass mh. First of all, this is a disk. Okay. Disk means I can consider disk as 2D. Let me draw a disk properly. This is a disk, a coin, something like that. I can consider this disk as 2D. Sometimes we do, and sometimes if you consider this height, however small it is, if you consider this, then it is 3D. Now what we have to do, we have to separate them mentally. See, these three are identical, these are kept like that, and the ground I have shown. Now we will separate them mentally. And also the ground we have to show it in dotted lines. Okay. Now we have separated it mentally but not physically. Now see, we will be analyzing the forces. Let me remove this. Let's start with this one. This is 1, this is 2, and this is 3. Let's start with 1. What is the force acting on 1? Definitely this will be mg. That will be acting from the center towards the center. Now it is touching two other disks, that is R2 and R3. I will draw the reaction force with blue. This is the reaction force. Say this is the reaction force from this one, this 2. So I will consider this as R12, that is, I will consider this as R12. So this is R12, and this one I will consider as, it is touching 3, so R13. Now this one I will consider. Now let's come to the object 2. This is touching surface 1, that is R12, equal and opposite reaction. There is mg, that is m2g, and I don't see any other force here because it is touching only two surfaces. And okay, now here there will be another force, that is normal reaction. It will be acting at this point. Same here, there will be a normal reaction. Let's say this is N2, let's say this is N3. This will be R13, exact equal and opposite reaction, and this will be mg. Now if you see one thing, This is a symmetrical proportion, so 1 and 2 and 1 and 3. This R12 will be equal to R13 and N2 will be equal to N3 because these are symmetrical. This is symmetrical. By the virtue of symmetry, we can say that R12 will be R13 and N2 will be equal to N3 because around this line this is symmetrical. Now see, I have written R12 is equal to R dash. Okay, one more force that we had not analyzed. See, exactly here, this 2 is touching 3 and this 3 is touching 2, so this will be R23 and R23 because these are also touching. So we have to remember that even after separating them mentally, we have to see these are also touching. See this part they are touching. So this is 1, this one is say 1, this is 2, this is 3, R12, R13, R23, the 3 pairs of reaction forces. So R12 I have taken as, say here, R12 I have taken as R dash and R23 I have taken here as R. So now this is our system. Now you have to comment that this is a stable system or unstable system. What I mean to say is that if I keep like this the coin, the discs like this, what will happen? Will it stay like that, or it will fall, or it will separate, or anything? What will happen? That you have to say. Okay, now you pause the video and think for 5 seconds or 10 seconds or as much time as you want and tell me what can exactly happen. Is it a stable or unstable system? Okay, I think you have thought about it. Now let me tell you, this is an unstable system. Why so? First of all, see here, this is mg acting downward. It is hidden here. Just this is mg. I'm showing you. This is r. Now see, this r has two components. One is normal, another one is tangential. This is normal. This is x and this is y. This is rx. This is ry. This r dash and r dash y will cancel each other. There is no doubt about that. These are symmetrical. This is x. R dash x and r dash x will cancel each other. This r dash y and r dash y, and from top to bottom there is mg. This 2 r dash y will be equal to mg. See, this first ball, this is r dash. This is also r dash. Now, this is r dash x. This is also r dash x. This is r dash y. This is also r dash y. Now this is mg. See, in the x direction, just see carefully. In the x direction, this is r dash x and r dash x are equal and opposite, and these will balance each other. So in x direction it is an equilibrium in x direction. In y direction also, there is mg, and this is r dash y and r dash y. So mg is equal to 2 r dash y. This is a possibility. This is a possibility that mg will be equal to 2 r dash y. So there is a chance that this r dash y reaction forces, these are adjustable forces. It depends on the other factors like how much force it is given, the contact surface, the inclination, etc. So we cannot determine from this one. Now let's look at either 2 or 3. Since they are symmetrical, looking at only one will do. Let's look at this one. See, mg will be equal to n, and it is not moving anywhere up or down the ground. So I can say mg is equal to n. Not just n, this is r dash. So there is, say this is theta. So r dash cos theta will be downward, and r dash sin theta will be this side. Now just tell me one thing. This is r dash sine theta and this is r. In the for the disk 2, I am having a force that is r dash sine theta and I am having a force that is r. But there is no force to balance them in this side. There is no such force. But here mg r dash, we can say mg r dash cos theta, mg and n, these three are balanced, but in the x direction this is not balanced. So this is unstable system. This is unstable system. You can do this directly without by having some practice. Like just see, it is not moving upward or downward, so it is balanced along the y-axis. Now x-axis you can see. Let's see this here. These are my forces. Now let's analyze only these two pair and these two. I am drawing one circle. There is this one, this is 2. I am drawing it here separately. And now this is R12 and this is R13. See, now if I take the component, this is R12x. This R12x and R13, these are not balanced. There is no force that will balance this in this direction. There is no such force. So it is unstable. Simple. As simple as that. Now, pulley and string system. We have already encountered pulley and string systems in constraint motion. Now let's learn a little bit deeper into that. See, for constraint motion, I have not mentioned the word massless pulley. Only in case of work tension method, I have said massless pulley, but in case of normal constraint motion like constant length method, contact point method, etc., I have not mentioned the word massless pulley. But here, massless pulley and massless string I will be mentioning. See what happens in a massless string. Suppose I am taking a segment of a string. At one end the tension is T1, the other end the tension is T2. The one end the tension is T1 and other end the tension is T2. Now I am assuming T1 is greater than T2, so T1 minus T2, that is the net force in this direction. So T1 minus T2 is equal to m into A. That is Newton's second law. Now T1 minus T2 is m into A. So, but if for massless string m is equal to 0, so T1 minus T2 will be equal to 0. So T1 equal to T2. So for massless pulley and massless string, tension is same throughout the same string. Please refer to the constraint lecture. Okay. Now why massless pulley? I'm talking about massless string, then why pulley? See, this is a pulley. Now to understand this properly, when I will upload the rotational mechanics lectures, you can see it there. For now time being, you may skip this, or you may see this further, or you may attempt to understand this if you know something about rotation. So the moment of inertia of pulley is I. What is moment of inertia? It is similar to the mass of an object, but in rotational quantities, the mass as well as the distance from axis both are accounted for the inertia part. So that is the moment of inertia. This is a very crude definition I can give you now. I will explain this later. Now, what is the net torque? See, due to this tension, this torque is anti-clockwise, and this due to this tension T2, the clock is clockwise. I am assuming T1 is greater than T2. So the net torque, I can say the net torque, that is this side because this is greater. So T1R minus T2R, that is the torque of T1R minus T2R, is I into alpha. These all things are there in rotational mechanics. So T1 minus T2, I am taking R down this side. So I alpha by R. For massless pulley, I is equal to 0. See, moment of inertia is proportional to mass and also the distance square. So if mass is 0, then there will be no moment of inertia, and I am assuming the pulley to be massless. So for massless pulley, moment of inertia is 0, so T1 is equal to T2. So you know, if the pulley is not massless, T1 won't be equal to T2. So if you have the same string, then you will be assuming the same tension. See, draw the free body diagram for this object, for this string pulley arrangement. Just before drawing for frictionless pulley, suppose this is a pulley. Now if I am wounding a string around it, just understand one thing: the string won't touch the pulley. Since there is no friction, the string won't touch the pulley, or the pulley won't roll. The string will slide over the pulley because there is no friction. Okay. Now let's do it. Now let's move a little bit faster because you know the basics. I hope so. See, this is very simple. Like, this is M1, this is M2, and there is a pulley. Say there is a pulley here, and this is fixed with a support. Now we will separate the objects. See, this object is for M1, this is for M2, and this is the pulley. M1, a force is acting, that is M1G, and the tension is acting upward. M2G is acting downward for this one, tension is acting upward. See, tension always acts away from the point of contact. Always. This I have explained in details in the tension work, that is part 4 of constraint series. You can see that. And here, this tension, for this part, the tension is acting here downward for the pulley, and here also T. Same string, the same tension, since the pulley is massless and the string is massless and frictionless. So, and from upward, from this support, I am getting a reaction R. So this is the free body diagram. Now, suppose from the constraint motion you can see, suppose I am assuming that this is moving down with an acceleration A. Now this is also move up with an acceleration A. This is common, and from the lecture of constraints you can understand this, why it is happening. If not, please go through once again. Now this is going downwards, this is going upward. By using Newton's second law of motion, I can say net force, that is M1G minus T, because it is, I am assuming the net force to be downward because acceleration is downward, is equal to M1 into A. This is for block 1. For block 2, T minus M2G, that is the net force, it is acting upward, that is M2 into A. Now by solving these equations, if we add them, we will get acceleration is equal to M1 minus M2 by M1 plus M2 into G. So this is how we can find the acceleration, and if we put the value of A here, we will get the tension also, that is T. And if we are asked to find the reaction force R, if we are asked to find the reaction force, that is R, say this reaction force, then that will be equal to R is equal to 2 into T, because T and T are downwards, R is upward, and this is not moving anywhere, so R will be 2 into T. So that was a simple case. Now let's increase the complexity further. Now draw the free body diagram of this wedge and pulley system. These type of questions we have covered in constraint series. Only the thing was that we were not concerned to find out the force or to worry about the force, except the tension. Tension was necessary, but except that we were not worried to find out anything. Now we are studying that force with a cause. So that could be called as the kinematics, and this is kinetics. This is study of motion with cause. Now let's separate the, as we know, see, there is the wedge, this is the block, we can see. Now let's separate. After separating, we can see there is a tension, there is mass mg, there is a normal reaction n, because there was a block, the block was like this here, so normal reaction n from the block. From this pulley the string was like this, so there will be T. Let's show you properly here. I'm drawing a little bit here only. This is T. T will act like this. Here also T will act like this. This mg will act like this. This is connected to the ground, so some n dash will be there, and this is connected here, so n will be there, n. So that's it. Exactly, that is the thing what we have seen. T m n dash. And here for this block I have shown, see, I have shown in dotted so that I can show the surface. N is acting like this, n, mg is acting downward, and T is acting like this, parallel to the surface. Now see, now what you have to do, now it is your job to see, I have already shown you how to frame equations and how to solve questions like that. So now it is your job to solve this question. This is the homework for you all, to solve this question and find out the acceleration of the wedge and the block. We have solved similar question in constraint series, so I would advise you to watch the constraint series once more, especially the contact point method, that is lecture 2. Then you will be able to solve this easily. There I have told you that after learning about free body diagram or Newton's laws of motion, you can solve these questions, and I will expect that you will write the answer in comments. Okay. Now free body diagram with friction. See, reaction force contains horizontal component called friction. Reaction force contains two components. One is horizontal component, one is vertical component. See, vertical component of R is called normal reaction. Let me do here. See, the surface, if I can draw the surface of any, say, if I can draw the surface of any object or any object, then no matter how smooth it appears, it contains some aberrations or something like that. So now if I put any object here, now this object, definitely it will touch a surface that is not straight. This won't be the case. It won't be straight like this, but it will be having some angle with the horizontal, say this will be touching this part. Now this reaction force will come something like this. I hope you got me. This reaction force will become something like this, and this reaction force will be having two components. One is horizontal, that will be friction, and the vertical one will be normal reaction. Exactly, this is what is written in the textbook. The horizontal component is friction of normal reaction. So I hope now it is crystal clear to you what is friction and what is normal reaction, and how are they related to the R or reaction force. Okay. See, I have already shown the same thing. Here this is R and this is R, and that R is resolved into two components. Now show the forces acting on the object. This is a rough surface I have given you, and this is the block is kept on an inclined plane. Now this is very simple. See, one thing I have to tell you, that is friction opposes relative motion. let me write it down. Relative motion. Friction opposes relative motion. I will discuss this in details when I will be solving the problems of friction. And friction, I will briefly discuss the theory of friction. The objective of this lecture is only to make you aware how to draw the forces of friction, how to identify the direct forces of friction in the free body diagram. So I will give a brief lecture on friction also later. Now see, I have drawn in a dotted fashion to make you aware of the surface. Now mg will be acting downward, normal reaction will be acting perpendicular to the surface, and friction, see this mass m, why I said this relative motion thing, it will have a tendency to move downwards, to slide downwards, so friction will act in the opposite direction, that is upward. I hope it is clear now. Friction is upward because this body has a tendency to slide downwards due to gravity. So I hope things are clear now, and I will advise you to rewind the lecture and see those parts which you were not finding it clear, and please take any standard textbook and please practice the free body diagram, practice drawing free body diagram, because I have only shown you the examples, and you can master it only by practicing. And also look at the objects around you and try to analyze them by using free body diagram. So thank you. This was a long lecture, and I hope you have all enjoyed it. And please subscribe our channel and share this video with your friends. Thank you.